Okay, so what I'd like to do now is introduce a total synthesis that highlights both Evans' oxazolidinone and Andy Meyer's methodology. And the total synthesis is that of Borrelidin, which is an antibiotic, and it was isolated from a strain of bacteria. Now, the synthesis that I'm going to highlight is a 2003 total synthesis. And it was synthesized by Professor Emmanuel Theodorakis at UC San Diego and his postdocs and graduate students. The publication to this is an Orglet paper from 2003, and it's a really quick read. And what I've tried to do is condense the total synthesis into the next couple of steps. Now, this isn't the only synthesis of Borrelidin. There are numerous other total synthesis out there, but Theodorakis did a beautiful job at highlighting and showcasing Evans and Meyer's methodology, starting with Evans and finishing it up with Andy Meyer's methodology. So I'm not going to go over the entire total synthesis. If you'd like to read the paper, feel free to do so. Sac State has a subscription to Orglet, so you can download and print the paper yourselves. I'm just focusing on a specific part of the molecule. Let me go ahead and draw out the molecule itself, and then we'll talk about it slowly. It is a cyclic structure. It does look overwhelming because there are so many stereocenters to it. Okay. So here's the cyclic structure to it. We are only going to focus on the bottom half. I'll only discuss the bottom half of the molecule, because as you can tell, that's where all the stereochemistry is. And what Theodorakis does is he numbers his carbons from left to right. And if you notice, he's only focusing on the bottom 9 carbons, and that's it. So the bottom half of the molecule. Using Evans. Oh, oxazolidinones and Meyer's pseudoephedrins. That's our target structure. Our target structure is from carbons 1 to 9. Okay. And so what he does is, because it is in a cyclic form, he unwinds this cyclic form and he cuts the molecule to the bottom half and he unwinds the bottom half into a straight chain aliphatic system. So that when you unwind it, it looks as follows. And you can really tell that My stereocenters are going to be at carbons 2, 4, 6, and 8. That's where my methyl groups are, right? That's probably the most obvious, that that's where my stereocenters are at, besides 1 and 9. The other thing that's hopefully obvious is that the stereocenters at 4, 6, and 8 are different from the stereocenter at carbon 2. So you can tell, oh, this is supposed to be a methyl. I apologize. I wrote a 9. You can tell that these are all the same and this is different and it's on its own. So this becomes my target structure. This is what he aims to construct. This is a retrosynthesis arrow. This is not a reaction arrow. A retrosynthesis arrow denotes your target structure and the starting materials you are going to use to make your target structure. And in this case, Theodoracus started with commercially available materials, acid halide, alkyl halide, and of course, the oxazolidinone and the pseudoephedrins of choice. Okay, again, this is a retrosynthesis arrow, not a reaction arrow. These are all commercially available. Okay. He broke this synthesis or the synthesis of this target structure into 4 steps. And so that's what we'll do as well. And part 1 or step 1 is using David Evans' oxazolidinones. Now, he didn't have to start with David Evans' oxazolidinones. He could have started with Andy Meyer's because Andy Meyer's methodology is much more efficient than Evans' oxazolidinones. He could have started with Andy Meyer's, but he wanted to highlight both methodologies. And he could only highlight David Evans' methodology by starting with his methodology. Because his methodology is so limited, you need to start with it and then you move on with Andy Meyer's. Okay. So part 1 of the synthesis is using oxazolidinones. And he used this specific oxazolidinone, treated it with N-butylene. Don't forget, N-butylene deprotonates, added the commercially available acid halide. And this specific acid halide is going to be carbon 7 and 8. Now, you need to make sure that as you're doing your synthesis, you're looking at your target structure so that you keep track of the carbons. Well, how do I know that's carbon 7 and 8? And we'll talk about this as we're moving down the synthesis and as we're going through it. So you introduce the carbonyl compound to the oxazolidinone. There's carbon 7 and 8. He then treats this with LDA. And if you remember, you always form your Z-enolate. Let me draw that out for you. There's my Z-enolate. Nothing new. We've already know that oxazolidinones favor the formation of acetylenolate because of steric interactions. Nothing new. Now I can add my alkyl halide. And if you remember, this is my alkyl halide. And I'll call this carbon number 9. Now, what I like to do, because this molecule looks a little overwhelming to me, if you can work with this molecule and if you can see it in your head, by all means, what I like to do is I like to label this R prime bromide. I like to make things easier for me. I replace the R prime for my alkyl group, and I leave the bromide as is. Remember, the new alkyl group or the alpha alkylation is opposite to the substituent on the oxazolidinone. So my product should look as follows. Okay. Again, notice how my new R group and my substituent are opposite. And we talked about why they were opposite, right? The benzyl group is blocking the front side. The R prime group has to come in from the back. Okay. So now what do? Now, I want you to look at your target structure. Specifically, I want you to look at 7 and 8. And notice how the methyl group is the one that's wedged. So what I want to do is I want to rotate things around so that my methyl group is wedged. Again, this is where you have to see things three-dimensionally. If you read the organic letter paper that Theodorakis wrote, he doesn't rotate things around for you. He assumes that you know that once you rotate, the methyl group is wedged. So I'm just going to redraw this after rotating. So be really careful. The R prime group is now on the plane of the board. This is still carbon 7 and 8. And if I rotate and the R prime group is on the plane of the board, it pushes the methyl group wedged. If you can't see this, you have to come talk to me. It's really important that you understand this as you're going through literature. So now I've got my methyl group wedge at carbonate exactly like I wanted. The other thing I want is I want to replace this R prime group with the actual alkyl group I've got. So I'm going to redraw it again. And this is not what you're going to see in his orglet paper. In his orglet paper, he assumes you can do this all in your head. So please be careful as you're reading the paper. And I've got my carbons 7, 8, and 9 set. Again, go back and take a look at your target structure. Notice how it's set up. I've got the right side of my molecule set to go. The next thing that he does, he treats this with lithium aluminum hydride and water. Lithium aluminum hydride reduces carboxylic acid derivatives to primary alcohols. And this is all from lecture number 1 of last week. He then converts the alcohol to a mesyl system. And adds sodium iodide to form it into an alkyl halide. Specifically, an iodo alkyl halide. And this becomes my new alkyl halide. And I'm done with part 1 of my synthesis. Now we're going to move on to part 2. Well, Dr. Lucero, where does this go? We're getting there. Part number 2. Please notice that this new alkyl halide, despite the fact that it's primary, it is also beta branched. It can no longer do oxazolidinone chemistry. So now he turns and pivots to Andy Meyer's methodology. Okay. He uses the following pseudoephedrine. Again, all commercially available. And Bewley uses the same acid halide that we used for our oxazolidinones. This is now going to be carbons 5 and 6. So please notice how he is building the chain from right to left. So he finished at 7, has to go on and build the next 2 carbons. Couples the carbonyl compound to the pseudoephedrine. Apologize for that. Adds LDA, just like we did before. Just like before, you get the Z-enolate. Nothing new. Oh, don't forget lithium chloride in excess. So there's my Z-enolate. I'll label these 5 and 6 again, so we keep track of our carbons. I add the new alkyl halide that I just made right here. Now, again, please notice that bulky alkyl halide, right? This looks incredibly intimidating. How am I going to rotate this around, Dr. Lucero? This has stereochemistry. I'm trying to add stereochemistry to something that already has stereochemistry. Change it to a simple R group, right? Once you change it into a simple R group, that's your R prime. You can come back at the end and substitute the R prime for the actual alkyl group that's on it. Okay. Please notice again, I can only do Andy Meyer's chemistry on this because this is beta substituted. So I can only do that. And my product, if you remember, is always 1,4-syn. Syn product. Okay. My R group and my methyl group are syn to each other. I'll do the same thing that I did before. At carbon 6, the methyl group is what has the stereochemistry. So I'm going to rotate about 5 and 6. It's not a reaction. It's just rotating. So that my R prime is on the plane of the page. And if I rotate, my methyl group is wedged. Now what I can do is I can substitute my R prime for what my actual alkyl group is. And what I get is oh, excuse me, I want to keep the numbers in red so that you don't get lost. And you notice that you're slowly building the molecule from right to left. And so I've added my new carbons, 5 and 6. I reduce this to the primary alcohol. If you remember, there is a specific borohydride reagent to reduce it to the primary alcohol. And I do the exact same thing that I did in part 1. Treat it with mesyl chloride and triethylamine, followed by sodium iodide to form my primary iodo-alkylated product. And I'm done with part 2 of my total synthesis. This will be my new alkyl halide. Notice that it's getting bigger, it's getting more branched, but I'm setting the correct stereochemistry depending on the oxazolidinone and the pseudoephedrine that I use. Let's move on to part 3. Because our system, our iodo-alkyl group is getting bigger and more sterically hindered, we are limited to only using Andy Meyer's methodology. So David Evans no longer comes into play. We start off with the same oxazolidinone because remember at carbon 4, the methyl group is wedged. So I'm going to use the exact same oxazolidinone that I used in part 2. So part 3 is going to look very similar to part 2. Now we've got carbons 3 and 4 that we're introducing. And so you should be noticing a trend as we're building this target structure. The first thing that I've already mentioned is the fact that we're building it from right to left. And the second thing that you should be noticing is that you're building it 2 carbons at a time. And if you've noticed, I keep drawing the intermediates to remind you of what they look like. You're still forming the Z-enolate. I don't want you to forget that. Once you form the Z-enolate, you introduce your alkyl halide. And that's the alkyl halide that I made in part 2. And again, don't get overwhelmed. It's a huge alkyl halide. But what you can do is you can abbreviate it as R prime. You should tell me what R prime is. If you don't tell me what R prime is, I don't know what you're adding. R prime is that huge chain that I don't want to worry about quite yet. I just want to set the stereochemistry that comes with Meyer's pseudoephedrine chemistry. So once you add it, just like before, you will get the 1,4-syn product. Let me draw that out for you. And see how easy it looks, or not how easy it looks, but how less overwhelming it looks when you replace this whole thing with an R prime. If you didn't, then you'd have to worry about the stereochemistry at carbon 6 and 8 being correct as well, depending on how you flip the molecule around. And I don't want to worry about that. I want to worry about one stereocenter at a time. So once I've got this, remember, carbon 4 has its methyl group wedged as well, and it's facing down. So I'm going to rotate it. I apologize, should be OH. My R prime group is on the plane of the page, which is how I want it. Then that means that my methyl group is wedged. I should have drawn this in black. So now my methyl group is wedged, and I can replace my R prime with the designated alkyl group. So it becomes a bit repetitive after a while. Which is probably a good thing. Because if you keep seeing it, it makes more sense as you're repeating it, right? Just like before, you reduce it down to your primary alcohol using your borohydride reagent. I'm going to do it all in one step now. Mesyl chloride, triethylamine, or not in one step, but all in one arrow. I apologize. Because these get really tedious to draw out. And I have formed my new iodo system. Okay. So there's my new iodo system. All I need is carbons 1 and 2. But if you remember, carbon 2 is the carbon that has different and opposite stereochemistry to 4, 6, and 8. I can't use oxazolidinones, so I'm forced to use Andy Myers. Since this is the pseudoephedrine that gave us the methyl wedged, it's safe to assume that the enantiomer will give us the methyl dashed at carbon 2. So we're still using Myers pseudoephedrine chemistry. But now we're using the enantiomer from parts 2 and 3. It's still coupling the same way we were before. But now we're introducing our final 2 carbons, carbon 1 and 2. Just because we've changed our enantiomer doesn't change the first few steps, which are the coupling steps. And the formation of the Z-enolate. So there's my Z-enolate. That's methyl group. I now introduce my new alkyl halide that I made in part 3. Just like before, I'm going to simplify it for myself. This is my R prime group. I don't want to worry about that stereochemistry right now. I just want to worry about what I've got going on at the alpha position. And just like before, my new R group is going to be introduced as syn, specifically syn to the methyl group of the pseudoephedrine. If I want the R prime on the plane of the page, which I do, that means that the minute I rotate and put the R prime group on the plane of the page, the methyl group is now dashed. And if the methyl group is now dashed, I can now replace the R prime with the rest of the alkyl group that it represents. And you can slowly start seeing it. Or you can slowly start seeing the target structure. Remember, the target structure was a carboxylic acid. So they just do a simple acid hydrolysis. And you form your carboxylic acid. Pretty clever. And there's his target structure, built from right to left. So Theodorakis really had an understanding of these reactions. He was really creative. He understood what enantiomer to use to derive the correct stereochemistry after rotating the molecule around, if that makes sense. So he knew what enantiomer to use, how to design it, how to arrange the reactions in an efficient fashion. And he was really resourceful on what enantiomer to use to provide the correct stereochemistry in high yields and high diastereoselective ratios, which is pretty clever. I think total synthesis is probably one of, again, the hardest fields in organic chemistry, because you have to be pretty creative and really have to know how to break the molecule apart and highlight certain methodology. And he did a beautiful job at this. Again, it's a really quick read. It doesn't replace these huge bulky groups with R prime groups. So you kind of have to do that yourself. And that's what I tried doing here, so that you can see that, hey, even though I've got this huge alkyl group with a ton of stereochemistry on it, I don't really have to worry about it. All I have to worry is about one stereocenter, and that's it. And then rotate it so that it's on the plane of the page, and then introduce and replace it with what I had labeled it as. Okay. Okay, you guys, the next video is method number 3.